Our next part of the waves unit is going to be the Doppler effect. You should be a little familiar with this from earth science. The Doppler effect, we're going to define it as the apparent shift in wavelength or frequency, because if wavelength changes, frequency is going to change, due to the motion of an observer of a wave or the source of the wave. So in this particular example over here, there's a source, this S, that's moving to the left and giving off waves. So as it moves to the left, it gives off waves. On this side over here, where he's moving away from, okay, the wavelength seems to get stretched out, and on this side that it's moving toward, the wavelengths get squished together. So we're going to rate the wavelengths get stretched out on this side. So we have a longer wavelength. Remember, the wavelength is this crest-to-crest distance. So any between these two circles here is the wavelength. The frequency gets longer, or I'm sorry, lower frequency. Now for light, that's going to look redder, because red are the longest wavelengths. So it's called a red shift because it's shifted to the red end of the spectrum. And it's going to be lower pitch sound. If the person's moving toward, if the source is moving toward a person, the wavelengths get squished. So they seem shorter. The frequency is higher. This over here is going to be higher frequency than this. This is lower frequency. And we get a blue shift because the bluer colors are higher frequency and shorter wavelengths, so like blue, indigo, and violet are the shortest wavelength colors of light, and you would get higher pitch sound. Now there's some math that we can do with this. We're going to say F prime equals F times V plus or minus VO over V plus or minus Vs. We have a lot of little definitions to give here. F is equal to the actual frequency that's being sent out by the wave, or by the source of the wave. F prime is going to be the observed frequency. V is the speed of the wave. So for a sound wave, that's going to be about 340 meters per second. VO is the speed of the observer. And Vs is going to be the speed of the source. Then we got to decide on this plus minus thing. The way I do for that is this. if they're moving toward, then f prime has to be greater than f. The frequency increases, so the observed frequency should be bigger than this. So in that case, I would have, if I want f prime to be bigger, this fraction has to be bigger than 1. So I would have plus VO, because making the top bigger would make it bigger than 1, and VS would be minus. Okay, because if I want to make this fraction bigger than 1, I have to have a smaller number on the bottom. And then the opposite is true if you're moving away. F prime has to be less than f. So this fraction has to be less than 1, so I want to make the top small and the bottom big. So it would be minus for VO and plus for VS. So at the top of the next page we have a mathematical example of this. Siren produces a frequency of 7,000, so that's the regular frequency of this thing, is 7,000. We have a stationary observer, so that's telling me VO is 0. And the police car is the source of the sound, so that's VS is the speed of the police car. VS is 40. The speed of the wave itself, the speed of sound, is 340. And then we also have to figure out if it's moving toward or away. So it's towards. So if it's towards, I know the frequency is going to increase because moving towards is shorter wavelength. They're getting squished. That's higher frequency. So I know that f prime has to be greater than f. The observed frequency is going to be higher than the actual frequency that's being given off. So now I write out my equation. It's going to be f prime equals f v plus or minus v0 over v plus or minus vs. So I'm going to get that f prime equals, the original frequency is 7,000. V is the velocity of the source. For this case, sound is 340. The observer is stationary, so I don't have to worry about whether it's plus or minus. That's going to be 0. Yeah. And then I'm going to divide that by 340. And now I need to think about what I'm going to do with this velocity of the source, this 40. Well, I know I want this number to be bigger than 7,000 because moving towards frequency's got to be higher. Therefore, this number on the bottom has to be smaller, so I'm going to pick a negative in there, so it's going to be minus 40. So this tells me I get 7,000 times, on the top I have 340, on the bottom I have 300. And that's going to give my observed frequency of 7,933 frequencies in hertz. So it is a higher frequency than the original frequency, so it's going to sound higher pitched.